Greetings everyone, welcome to Side A, Side B. In this video, prove two corollaries of Thales Theorem. The overall plan, ladies and gentlemen, develop a line of thought supported by rules and theorems. So what's in our toolbox? How about straight up algebra and geometry? In our first video of the year, we proved Thales Theorem regarding proportionality. If you haven't already, we invite you to check it out, and then come back and join us. In that video, we referred to a paper about visual space as a metric, and then discussed the two possible ways to consider visual space. In this video, first, we'll discuss two possible ways of solving a mathematical problem, either by substitution or by componendo. First, an example. Use substitution to solve the system of linear equations x minus 3y equals 16 and 3x minus 2y equals 13 to see where they intersect. First, we want to choose one of the two given equations and solve for either of the variables x or y. It doesn't matter which one we pick first. Then, the result will be substituted into the other equation. The goal is to get a single equation with one variable on one side, a constant on the other. Sounds good? If so, let's make life easier. Choose the variable x of the top equation in terms of y. Then we get x equals 3y plus 16. We can now substitute this expression into the bottom equation. We end up with 7y plus 48 equals 13. Finally isolating, y equals -5. Very nice. Now we know the exact value of y. We can solve for the other variable x by substituting y into any of the original two equations. We get x equals 16 subtract 15, which just equals 1. Voila! Our solution set is x equals 1, y equals -5, which means this is where the expressions intersect on a graph. Is this the case? Let's check our work. We solved for y in terms of x for both equations. The top equation for y is the red line. The bottom equation is the blue line. The domain of x doesn't show. You don't have to trust us, folks. And it's easy enough to verify yourself. Our solution set checks out. There's one example of the substitution method. It's definitely a valid method that we've used many times. But let's put substitution under the microscope. Let's see how it does on a more challenging problem. And then compare it with a different method. As it were, substitution or componendo. Let's begin. Here's what we gave AI. Express 5a minus 3b in terms of a plus b over a minus b. We'll explain why in a moment. We only need to discuss the solution briefly. So here's what it offered. How to solve the problem by the method of substitution. Underlined yellow. Okay, fair enough. In step 1, let x equal a plus b over a minus b. Step 2. Solve for a in terms of b and x. We can use straight up algebra to do that. See that? It ended up as a equals b times the expression x plus 1 over x minus 1. Step 3. We know we substitute a into 5a minus 3b right to the white box. Then replace x with a plus b over a minus b. Then, check the work. As it turned out, it checks with the yellow. Then, the white box holds. But now, we want to find the following. First, by separating the fraction to get the equality. Then, multiply both sides by the denominator d. Then, divide both sides by 2b. We get the white box, which is what we wanted. So there's another example of substitution, and actually a nice study by AI. But is there an easier method? So here's the original problem. If a over b equals 3 over 5, find a plus b over a minus b. Then, in column 1, case 1, we cross multiply to get 5a minus 3b equals 0. We know AI offered the substitution method to solve case 1. Before we formally discuss it, in case 2, we'll use the method of componendo. Then we have a plus b over b equals 3 plus 5 over 5. Next, in column 2, we cross multiply. Notice the yellow arrows was just equivalent to adding 5b to both sides of the equality, which doesn't alter the equation at all. Then rewrite both sides by the following way. Now we can subtract 4b from both sides, which is nice. Do the following. Subtract the other 4b on both sides, factor of 4, and then subtract the 4 times expression on both sides. Finally, divide a minus b on both sides to get what we want in the white box. To check the work, a equals 3 and b equals 5. We have then 8 over negative 2 equals negative 4. Checks out, nice. So what do you think? Was that easier? We think so, but the substitution method was a good study. Also notice we added 10b to the entire equation, but then canceled 8b. So we could have just added 2b to the entire equation. What you might have guessed already, the Componendo rule simplifies the relationship between two proportions. We used it in our last example, and we got the expression a plus b for free. All we needed, find a minus b. The Componendo rule states, if a ratio a over b is equal to the ratio c over d, then adding the denominator to the numerator of both ratios will maintain the equality. If the said equality, then a plus b over b equals c plus d over d. Let's prove it. To prove an if-then statement, the if is the hypothesis. We have to prove the then is true. Then consider the following ratio equality. Then add 1 to each ratio. Next, find common denominators. We get a plus b over b equals c plus d over d, which is what we wanted to show. Now we can refer to Thales Theorem and Componendo to prove two corollaries of the same theorem. We want to prove the ratio equality in the white box. AB over PB equals AC over QC. We have the triangle ABC, and referring to the definition of parallel lines, the line PQ is parallel with the line BC. Also, the following ratio equality in the blue box by Thales Theorem. Next, in column 2, add 1 to both sides. Then find common denominators. By Componendo, we have that AB over PB equals AC over QC. Since the white boxes match, we are done. Nice. Proving Corollary II is very similar. We want to prove the ratio equality in the white box. AB over AP equals AC over AQ. We just refer to what's already been said regarding column 1. Next, in column 2, we refer to the invertendo rule, which states if the ratio of two numbers is equal to the ratio of the other two numbers, then the inverse of the ratio of the first two numbers is equal to the inverse of the ratio of the other two numbers. Mathematically, it means if A over B equals C over D, then B over A equals D over C, and we don't have to prove it. We use the rule to get PB over AP equals QC over AQ. Then do the same steps as before, such as add 1 to both sides. By componendo, we have that AB over AP equals AC over AQ. Since the white boxes match, we are done. Like we said, we wanted to prove the corollaries of Thales' theorem. We thought one video would throw off the proportion of work. So one more video to prove the last corollary and do a study on how Thales could have used it to measure the height of a pyramid. Since the proportion to an exit is equal, we are out of here. Until next video, folks.